Hello everyone, welcome back. Now, in the previous two videos, I introduced you to auxiliary functions, and in particular, we discussed Lyapunov functions. And then in the previous one to this, we talked about sum of squares polynomial optimization, where we actually showed that there are computational methods to find, say, Lyapunov functions if we know the right-hand side of the dynamical system, and if it's polynomial. Now, what I'd like to do in this lecture is show you how to implement these auxiliary function methods with sum of squares programming, but directly at the level of data. And the result here is going to be a method that could say, find Lyapunov functions based on the data that you provide. This would give you global stability of a system only knowing limited information about that system. Or what you could also do is implement the bounding framework for the time averages, this ergodic theory problem that we had that was also introduced with Lyapunov functions. You could implement these methods based on only limited data. Think about the potential here, right? You could have very expensive to produce data, and you produce a little bit of it, and you can find information about the global system dynamics. And everything here comes down to the Koopman operator. Now, one thing that we've learned throughout this lecture series is that the Koopman operator is doing a lot of heavy lifting in this data-driven framework, and it's not going to stop now. In particular, what I'd like to do is I'd like to introduce a more general version of the Koopman operator. I'm going to use K here. Remember, the Koopman operator acts on what we call observables. Now, observables are functions. I'll just use phi as my stand-in for this function from the state space into the real numbers, right? It takes a measurement of the state of the dynamical system. What is the energy? What is the momentum? What are the glucose levels, etc. Now, the most general way of writing the Koopman operator is to write it in terms of how far you want to go forward in time. So here I have a time step tau. It is acting on these functionals. And for a general Markovian process, so dynamical systems, these are Markovian processes, but these can also apply to stochastic systems if you want, and we can here in this. It will be the expectation of phi at x of t plus tau given x of t is equal to x. And sorry, this is at x here, pardon me. So the Koopman operator takes in a function, and for each value of x, it returns the expectation of that observable in the future, 1 tau time unit ahead. Okay? So now, of course, as we've seen before, if this is a discrete time dynamical system, so tau would just be equal to 1. You're sort of taking one step into the future. There's no expectation here if it's not a random system. And this is exactly what we saw, right? So for a finite dimensional discrete time dynamical system, this just becomes function composition. This is what we learned when we talked about approximating the Koopman operator. But this also works for, say, continuous time dynamical systems. And it also works for stochastic differential equations. Now, the important thing to note here is, remember that Lie derivative that I showed you in the previous few lectures? L? Well, it turns out that the Lie derivative is the generator, so is the generator of the Koopman operator. And what I really mean by this is that in continuous time, the Lie derivative is given by the limit as tau goes to 0 of the Koopman operator. Maybe I should have put a tau down here. Again, I just want to emphasize this. Minus phi divided by tau. Go back and take a look at the definition that I gave you previously for the Lie derivative. You'll see that it had this expectation term in it. All I'm doing is replacing that expectation term right here. Now, if you're familiar with differential equations theory or dynamical systems theory or even just abstract algebra, you'll recognize these terms as L being the infinitesimal generator of the process. Informally, so I'm going to write this informally because there's some mathematical details that are being left out for this to actually hold uniformly. But it really sort of tells you that k tau should be thought of as e to the power of L times tau. Now, of course, L is an infinite dimensional operator. So this exponential you have to be a little bit more careful with, right? It's not just a matrix exponential. But informally, this is what we're having here. And then if you sort of plug this formula in, that's where you can see where this where we get this sort of generator property. Okay. Now, of course, for discrete time, right? For discrete time, we don't have to take tau to 0. Tau is going to be 1. So really, the Lie derivative in this case is just going to be, Koopman. I'm not going to write 1 down here. I'm just going to say Koopman of phi minus phi, discrete gradient, right? And this is for discrete time. Now, okay, but what's the purpose of bringing all of this up, Jason? Well, the purpose of bringing all this up is that I gave you methods for approximating the Koopman operator, right? We did it in 2 different ways. We did it with extended dynamic mode decomposition, and we did it with kernel methods. But take a look at these formulas, right? If I can approximate the Koopman operator, then I can approximate the Lie derivative. But now follow the chain of command, or the chain here. If I can approximate the Lie derivative, I can implement the auxiliary function methods. Remember, the Lyapunov function is nothing without just a negative Lie derivative. But then if I can approximate the Lie derivative, I get auxiliary function methods. If I get auxiliary function methods, I get macroscopic information just from data. So this is amazing in my opinion. So let's take a look. How can we do this? Well, what I'm going to do is I'm going to guide you through some methods laid out in a paper by myself and Giovanni Fantuzzi. So there might be other ways to do this. In particular, Alex Maury has some really nice ways of dealing with these kind of problems as well, absent the polynomial optimization framework. But here I'm going to show you, coming from my own work. Of course, I'm biased on this. What I'm going to do is I'm going to create 2 dictionaries. Remember, EDMD deals with 1 dictionary. I'm going to call these dictionaries DP and DQ. They're going to be, since we want to use polynomial optimization, it's going to be polynomials. In this case, let's go up to L. And then I'll also introduce DQ. And you'll see where this comes from in a moment. But imagine these are sets of polynomial functions. And I think I want to use M for this. Yeah, so L and M are the sizes of these dictionaries. And of course, let's do a little bit of shorthand here. I'm just going to call this vector of components in here P with the vector over it. And I'll call this Q with the vector over it, just so that I can make the notation a little bit easier. And the assumption here, okay, so we need an assumption. My assumption is that, so assume that the span of P is inside the span of Q. So again, if you're thinking about polynomials here, P might be all of the monomial terms up to some degree. Q is just up to a higher degree, okay? And what this really tells you is that there's a way of mapping all the terms in Q into P, and I'm just going to call that operation capital theta, okay? So it's just a matrix. It just identifies which terms in Q are present in P, okay? That's just all that is telling you. And what this is really going to be trying to do is capture the overflowing property of the Koopman operator, right? This composition that you would get, or this multiplication, f dot grad operation, it will add more polynomial terms, right? It'll increase the degree of your system. And so this is what you're trying to capture if you want to do really highly accurate approximations of the Lie derivative. Now, the reason we used only 1 dictionary for EDMD is because we were interested in eigenvalues and eigenvectors of that problem, right? So we need a square matrix. Here, we don't really care about a square matrix. We care about accurate approximations. And so we're just going to make 2 different dictionaries, potentially. You could keep them the same if you wanted. Now, I'm going to take some data matrices. So here's my data. I'm going to organize it in huge matrices, just like we have done with Cindy, with EDMD, with DMD, with kernel DMD, you know, all of these methods. And it's going to be in real space, and there's going to be d-dimensional space. There's going to be n snapshots. Remember, the columns of these things are called snapshots. Here's what I want. The assumption is that all of these snapshots of x are found tau units into the future in y, okay? So tau units. And of course, if this is a discrete time system, tau just needs to be 1. So, you know, what's happening now, what's happening next. But if it's a continuous time system, this is the sampling rate, right? It's how quickly you're getting the, it's your time step in your data. So then I'm going to make these nice big matrices. I'm going to say, let capital P be, and then this is where things get kind of weird. It's going to be my vector P evaluated at the first snapshot in Y, and then all the way over my vector P evaluated at my last snapshot in Y. Okay, so again, data going across the rows, dictionary elements going down the columns. Just for accounting purposes, this is going to be an L by capital N matrix, okay? L rows, capital N columns. Similarly, let's introduce another one. We're going to call it Q, which you can probably guess. It's going to be my vectors in the dictionary Q evaluated at the X data points. We don't need this. We don't need a comma. xn. And again, let's do that accounting. This is going to be an M by capital N matrix. Okay? Now here, what we can see is that we can approximate the Koopman operator. So let's say approximate Koopman. And my approximation of Koopman is going to be, I'm going to call it K tau. Okay, so here I'm just a script K sub tau, which is going to be computed basically the same way that we were doing all these computations. It's with a pseudo inverse. It's P times Q pseudo inverse. And that is going to be an L by M matrix, okay? So again, it doesn't have to be square. This is probably the hardest part, organizing your data. This takes a lot of thought to see sort of where we got this from, why each one has to have, you know, forward time step and your current time step. But for the time being, we could ask ourselves, how does this act? Well, this function, K, so K tau, maps the span of P, which we call the expansion dictionary, because this is what we would maybe expand our Lyapunov function in, into the image dictionary, Q, by, if you take an element in the span, so a vector of coefficients dotted with the elements in the span, this is going to be mapped forward by this vector C dotted with the matrix K times tau against the vector Q. Okay, so again, it's a little bit more complicated than maybe we saw with EDMD, but of course, you know, it does more work. It's sort of better, right? It's more complicated, but it gets us further. And then the Lie derivative here, well, the Lie derivative comes from this approximation as well. We can call the Lie derivative L sub tau, and it's just going to use this computation right here, okay? But without a limit, of course, right? It's a discrete derivative, essentially, but it's going to be K tau minus my big theta, and my theta was my mapping between P and Q, and then divided by tau. And so similarly, we think about how this thing acts as an operator, you're going to say that L tau operates on P belonging to this span in the way that you get the coefficients C dotted with L tau times Q. Same thing as we saw up here. So this, right here and right here, these are complicated. I'm not saying that it's easy. It takes a lot of thinking, and in particular, it takes a lot of just doing it in MATLAB, for example, to figure out sort of where these formulas came from, why this arrangement has to be put together. I mean, it took Giovanni and I a little while to figure it out. But let me tell you something amazing about this method, okay? Look at my original Koopman operator up here. It is very sort of complicated. It's very general, right? Here's the thing. We prove in our work that if you provide data, but I don't know if it's deterministic or stochastic, it doesn't matter. You'll still converge as the amount of data goes to infinity to the correct Koopman operator, and as tau goes to 0 to the correct Lie derivative. That means that I can implement this method on both stochastic or deterministic data without knowing, right? It's still going to work. It's still going to give me the right answer if I've got enough data. That is awesome. That is a fascinating property that sort of falls out of these proofs. And it's something that we're going to explore with some computations later on. But let's take a look at something simple. Let's discover a Lyapunov function from data. Here's a nice little implementation with a very simple planar discrete time dynamical system, okay? So you can see it really only has one nonlinear term in it. This is a discrete iterative system. That means that our tau is going to be 1 in this case, right? So we're dealing with discrete gradients. It's deterministic and it's globally stable. That is, we know that everything converges to 0 for this system. So what we're going to do is we are going to collect a little bit of data from the system. We are going to use that data to discover the Lie derivative. We're going to take the Lie derivative. We're going to try and find a Lyapunov function by replacing the real Lie derivative that has to be decreasing for a Lyapunov function with this data-driven Lie derivative that comes from this sort of verified or augmented extended dynamic mode decomposition method. So here's some parameters that we're going to take a look at. We are going to use a dictionary up to degree 4 of the P dictionary. And we're going to use the Q to be up to degree 6 in this case. We're sort of just making it bigger. In fact, you can make it as big as you want, but 2 is the smallest that you can make it with to get good results. So I could do +4, +8, +15, whatever. The results are going to be almost exactly the same, but 2 is really the threshold. And I want you to think about why that's the case, actually. These are just for some computational implementation. We can come back to them later if necessary. But here's what we're going to do. We're going to gather up, in our case, 100 data points, so not very much, right? Maybe slightly realistic if this was a system where it's hard to generate. We're going to generate up a whole bunch of points in the interval -2 to 2. And let's take a look here. Our y data is going to be 1 time step into the future. So let's run this. And now what we're going to do is we're going to create those big P and Q matrices. Okay, so just like I showed you on the board, it was down here earlier. Now here's my approximation of my Koopman operator. As you can see down here, I have my approximation of my Lie derivative. You can see that these are sort of complicated, but that's because of this action that I showed you for these approximations of the Koopman and the Lie derivative matrices, or as matrices. Now what we're going to do is we're going to create these, or try and find these, or a Lyapunov function using the method that we've already seen from last lecture. Here we're asking for sum of squares representations of, this is the first condition, basically the sort of open up, that it's non-negative, and here again, epsilon is equal to 1. Here's that x1 squared plus x2 squared, the coercivity condition, the strict non-negativity condition. Here, L, well, that's our Lie derivative. We want the negative of the Lie derivative to be positive. Remember, sum of squares is always talking about positivity. And again, we have this strict inequality coming in here as well. So let's take a look. Let's actually see what we get. Here it's running and successfully solved. So we were able to identify a Lyapunov function from this data. And here the clean from the very beginning was just setting coefficients that are very small to 0 so that it's easier to interpret this thing. And here are the coefficients of my Lyapunov function, okay? So in this case, it has no linear terms. This is this is the constant term, x1, x2. And then here's the quadratic terms, and there is only one quartic term that shows up in this thing. Now, the next thing you could ask yourself is, okay, Jason, that's wonderful. You found a Lyapunov function that's fit to like 100 data points, right? Is this actually a Lyapunov function for the dynamical system? Right? If I actually take the Lyapunov function that I discovered and I put in the exact Lie derivative using these dynamics right here, can I verify that this was actually a Lyapunov function, or did I just get a false flag here? Well, that's what the next piece is doing. So we're actually just checking sum of squared. It's just a feasible or infeasible optimization problem. And what you can see here, again, successfully solved. We have actually discovered a true Lyapunov function from the data, right? So we weren't just, getting false information. What I also want to remind you of is my data points were randomized. So I didn't get to sort of select, the data in such a way that made it work for you. You can also download this yourself. You can play with it. You can see how little data you can get away with, how much data. If things get better or worse, you can increase the size of the dictionaries. All this stuff, it's the only way you're going to learn it is if you do it yourself. Now, before we finish up, I would like to do one more example, and I would like to look at these time average bounds. And here's what I'm going to do. I'm going to do it again for a discrete time system, but remember, I told you we could do this for stochastic systems. So let's look at the random logistic model. Here it's just a scalar, right? So it's just one. I'm not going to put x1 or x2 here because it's just one quantity. Remember, the logistic function looks like this, right? And if we increase the value of lambda, we can generate chaos, right? Lambda goes between 0 and 4. But I'm going to make this system random. I'm going to choose lambda from the uniform distribution on 0 to 4 at every single iteration. So lambda is not fixed. It's being randomly selected, and then you apply the logistic map. So really, we should think of this as being dependent on n. But this is genuinely a stochastic system now. And I'm going to try and bound the time average. So my quantity of interest here is just going to be the state itself. Okay, so x. So let's go ahead and let's take a look at this implementation. Okay, so I do everything with Chebyshev functions here instead of the monomial basis. That just means my dictionaries are in terms of, instead of 1x, x squared, x cubed, it's the Chebyshev polynomials, and that's just because they're behaved a little bit better numerically. So you can go into this, you can check it out, you can have some fun with this. Here again, I have my dp and my dq. My dp is going to be 2. I called it alpha for some reason here. My dq is going to be 2 plus 2. So this df is adding it in, or sorry, multiplying it in because we have a discrete time system. What I really want you to notice here is this takes a lot of data, okay? In this case, I have 1 million data points. You can see in the book or in the paper that this comes from, for these random systems, you need a lot of data. And briefly, the reason for that is because you need these expectations to converge. So you need to really explore a lot of the parameter space as well. This is very different than the Lyapunov function setting from the previous example because that was like 100 data points. But nonetheless, this still works. So let's take a look at it. I'm setting up my data. I'm gathering all my data. Here I'm building my P and Q matrices. It's a little bit uglier, but that's just because I want everything to drive well with my Chebyshev polynomials. And then Here's some lower bounds. Let's actually take a look at these things. Let's see what we can get. So here is our numerically computed upper bound, about 0.375. Remember, that's with degree 2 polynomials. If you take that million data points and you just average this thing, you get about a quarter. Actually, Giovanni and I formulated a conjecture that the exact time average of this thing should be about a quarter, and that's what you're seeing highlighted here. And then you can also look at lower bounds as well, just by reversing those inequalities. We talked about this for the Lorentz system. The numerical lower bounds are very close to 0, and that's good because the exact lower bounds are also close to 0, because 0 is a fixed point of this system. Let's actually increase this alpha term here. Let's go up to a degree 8 dictionary. Let's run the whole thing, and let's take a look at what we can see here. It takes a little bit longer because it's a longer system, or it's a larger semi-definite program to work on. Here now we can see that the upper bound is coming way down, so we're at about 0.28, whereas again, remember I told you that empirical average is around a quarter. So we're getting closer. We're off by about 0.03 now. In particular, if we had the exact Lie derivative, you can prove that these lower bounds are going to, or these upper bounds are going to converge onto this maximal value. So in this case, onto 1/4. But again, something we observe is that with these stochastic problems, it happens very, very slowly. So it's typically for stochastic problems, you need a lot of data to get good approximations of the Koopman operator, and you need very large dictionaries in order to get good upper and lower bounds on these time averages. But nonetheless, it works. And what I want to emphasize to you is, yeah, I used the Chebyshev polynomials instead of monomials, but that doesn't affect the implementation. There was nothing here that required me to tell it that my data was stochastic. Okay? That's what I want you to keep in mind. I got the Lie derivative just by doing the same old Koopman approximation with the pseudo-inverse. Nothing fancy, no pre-processing. I can apply this to stochastic or deterministic systems, discrete time, continuous time, no change. It's all there. It is at the ready for us to find macroscopic information from sort of microscopic information, just little data points. When we come back in the next video, we'll actually see how to use these methods for control. So I'll see you all in the next video, everybody.